Yay. All right, just getting everything set up. Okay, well, maybe, let's see, we're like 1 minute early, but I'll just sort of start. Today the plan is to discuss WKB. We started that last time, but today we'll continue that discussion. And then today the main event is to discuss tunneling in the WKB approximation, and then to do an application, which is alpha decay. Sort of the most famous application of WKB, alpha decay. All right. So, all right, let's see. This, okay, so I introduced WKB to you guys last time. And what I said was that the whole point of WKB is to solve the Schrodinger equation, H psi equals E psi. That's always the whole point, most often in this course. That comes up a lot in quantum mechanics, solving the Schrodinger equation, where H is the usual thing, kinetic energy plus some potential. And the idea is that we have some complicated potential that we don't know how to deal with. It's just too hard for us. We're just not smart enough to deal with it. So we come up with a really gross approximation. And so we notice that if the energy of our particle is big, and at the same time, the potential is slowly varying, which really both mean the same thing when you think about it, then what we notice is that we can make some approximations that allow us to derive the solution of the Schrodinger equation. Then we see that the solution, the energy eigenstate, can be written like this: some constant times square root of k of x times e to the plus I integral from 0 to x k of x prime dx prime plus b square root of k of x e to the minus I 0 to x k of x prime dx prime, where k of x as a function is our old friend, the wave vector, 2m e minus v of x over h bar. And that's it. And that's really nice. So that's the end. That's the answer. That's the eigenstate. So that's the hope. That's why it's nice. That's the whole point, is that we don't have to solve the Schrodinger equation anymore. The Schrodinger equation is a really hard differential equation, and we're just throwing out all the details, and we're just saying, boom, here's the solution. So that's the whole point. That is the WKB approximation. And we like it because it makes everything really simple. But of course, it's an approximation. It's not always correct. And so there's two famous examples. There's two famous applications of WKB. I mean, there's many. You can use it in many different ways. Some people use it a lot, others not so much, but I've never used it all that much personally, but I have seen it used many times. And the two famous examples are one, bound states, bound state energies. You can use it to get the bound state energies. And it comes from doing this little integral that, and we derived this last time. You have these 2 points, 2 limits of your integral, k of x dx equals n pi. And sometimes there's a little delta offset. And these limits of integration, the limits of integration are the classical turning points. And the classical turning point, can anyone give me the derivation of a classical turning point? What is a classical turning point? Do any of you remember? Just blurt it out.
That's when potential is equal to the energy of the particle.
The total energy, exactly. It's like a ball is rolling up a hill, it stops. That's the turning point when total energy is equal to potential energy. Exactly. It's where, it's the location in space where the total energy is equal to the potential energy. Okay, the turning point. And I will just mention, and this is something I glossed over, I derived this, for a very simple case where everything equaled n pi, and that was very straightforward to see in the example that I used. But there are some subtleties, and I glossed over this, but I will mention it now. Sometimes subtleties due to details of the classical turning point. And this leads to something that is called the WKB connection formula. And sometimes you get a small phase offset. That's the thing that I call delta here. So sometimes you get a small phase offset there due to the details of the turning point and these WKB connection formula, plural. And it's really just a big topic of just lots of tedious detail where you just get for not much extra insight. So I'm skipping all that. And so the idea is that you just, for this little thing that you do, for this connection formula, just look it up in a book. Look it up in book. And the reason I'm glossing over it is because I have never used the WKB connection formula once ever in my life. I have never seen them used once ever in my life. And I have seen them derived, and it's really horrible and tedious to derive them, and you get very little for all that effort. And so I'm just not going to bother doing it. But I will mention that they exist, and that sometimes, maybe for some people, it's the most important thing in the world. That's the nature of physics. Just in my life, I've just never seen it used. But sometimes you might get a little tiny phase offset there. And so I will just mention that that exists and just look it up in a book and use it without having to worry about where it comes from. It's just not worth it, in my opinion. But you might have a different opinion, so that's okay. All right, and so the bound state energies is the one example where we used it, and that was nice. And then, but the second example we did not do yet, and we're going to do it. And the second example is tunneling. And in fact, this is really the more important example. This is the most important use of WKB, in my opinion, because I've seen it used a lot for tunneling. Most important use is tunneling. Okay, so let's do tunneling. So let's do WKB tunneling. The WKB approximation for tunneling. This is the most important use of WKB. This is where WKB shines. All right, and so this is the problem. Here is what we're trying to solve. We have some potential. We have some barrier, some weird barrier. And what I'm plotting is V, the potential, as a function of x. And what we do is we shoot a particle at this barrier. This is the barrier. And the barrier might have some really weird complex structure, as you see how I've drawn it. And we shoot a particle with some energy. There's the energy. And we shoot that particle at the barrier. And then we ask the question, what is the probability to get through the barrier? That's a very important question, because it's something that we can experimentally test. You can take an electron gun and shoot a bunch of electrons at some barrier and see if they get through. So this is something that we can test in a laboratory. So this is very important, happens all the time. And it's the basis of many devices that are the foundation of modern technology. Okay, and so this is a really important problem. And so the main question, let me just write it, is the main question that we're trying to answer is, what is the probability to get through the barrier? But the language that we use in quantum mechanics is we say, what is T of E? And that's the transmission coefficient that you have seen before. And so what the heck is this T of E? Well, you have seen this problem before. Last semester you've seen it, and I even talked about it today, or this semester a little bit, because it's like scattering. I mean, you know, the barrier penetration problem is really a one-dimensional scattering problem. And so what we do is, you know, this problem, you've seen it before. You know that on this side, on the left-hand side of the barrier, we shoot in a particle, and that particle is like a plane wave, e to the I kx. And it has some probability to reflect. And the reflection, the wave function that corresponds to reflection, there's a component r e to the minus I kx. And then there's also a component of the wave function that represents the amplitude to penetrate the barrier, which looks like this. And it's t e to the I kx, where k is our old friend. You guys remember what k is? Just decide the best place to write stuff. K is equal to square root of 2m e minus v over h bar. And then when we write it like this, which is a familiar thing for you, then we see that the probability to get through the barrier, the transmission coefficient T of E, is equal to what? When I write the problem out like this, what is T of E equal to, big capital T of E? Tell me. This is a question for you. What is it? Look at the stuff I wrote. In terms of the, here's the trick. In terms of the quantum mechanical wave function, Because if we can find because what I've written out here, that's the eigenstate, right? All these little wiggly stuff I've written, those little wiggly lines, those represent the eigenstate, the solution of the Schrodinger equation for this problem. And once you have the solution for the Schrodinger equation, then the transmission coefficient is embedded in the eigenstate. And so I've wrote the eigenstate right there in front of you. And I'm telling you that the transmission coefficient is embedded within it. And I'm asking you to pull it out and tell me what it is. So look at that wave function and tell me what is the transmission coefficient, the probability to get through that barrier.
Is it a little t?
Good. Close. That's good. Very good. That's very close. It's almost little t. What are you missing? One small thing.
Is it squared?
Right. Right. Because remember, wave functions are not probability. They are amplitude, which is a weird concept. You know, what the hell is amplitude? Well, that's another, philosophical discussion. But wave functions are amplitude, which can be complex. And to get probability, you have to square the amplitude. All right. So t is the wave function thing, the amplitude, and the probability is always going to be amplitude squared. So it's t squared. So that's good. You got it. T squared. Okay. So so you see that the whole problem boils down to getting t squared. But how do you get t squared? How do you get that? You guys remember? You did it last semester. Like, for example, here we have, I'll call this spot x1, and I'll call this spot x2. And we have different regions. You can see we broke it up into regions. On the left, we'll call that region 1. In the middle, we'll call that region 2. And on the right, I'll call that region 3. And how do you get t? You guys remember? What's the trick? Like, what do we do mathematically? How do you get t? You did it. You've done it a million times. You might not remember because maybe you haven't done it for a while, but you did do it many times. How do you get little t? Tell me. What's the trick? What's the math that you have to do to get little t? This is something that you always do to solve a differential equation. Someone gives you a differential equation. In this case, it's the Schrodinger equation. You solve it, you get the functions, which are the little wiggly lines I wrote down. But that's not the full solution. To get the full solution, you have to take one more step to solve the differential equation. What is that last additional step?
Is it boundary conditions?
Exactly. That's exactly right. You have to match the boundary conditions, which is that psi and the derivative are continuous. And you've all done that. And that's how you get it. Continuous. Well, I didn't quite spell it right. Close enough. Okay, right. That's what you got to do. Okay, good. And so that's right. But now you're confronted with the problem because you see, I wrote down the solutions. I just wrote them down, on the left and the right, because they're easy. Because I have a flat bottom. Because you know that if I have region 1, psi in region 1, psi of x, you know that it's really easy to write the wave function in region 1 because the potential is so simple. It's just a 0 flat bottom potential. And so you know immediately that in region 1, I can say that the wave function is, I'll just say some constant a times a forward wave, e to the k1 for region 1, plus some constant b times a reflected wave. This is the notation I'm going to use today, where k1 is just the energy, because the potential is 0, right? And you know that similarly in region 3, I can just write down the solution because it's so simple. You can solve that differential equation in your head because you've done it a million times. You know, it's just f, I'll call it f, e to the I k1x. Because, and it's really easy to write because the potential is 0, where once again, I have the same k1. But the problem comes for region 2. What the hell is psi in region 2? Because you guys solved this problem last semester and it was really easy in region 2 because you guys remember that in region 2, you know, you had, like when you did this problem last semester, you solved it for this problem. Flat top potential, right? And you had the energy here, and then you knew that I had a wiggly guy here and a wiggly guy here, and then a wiggly guy here, right? X1, X2. And then in the flat bottom part, it was because in the flat top part underneath the potential is really easy because that potential is just a flat constant. And so you know that in that region, you had then 2 other solutions that were very easy for you to derive. What were they? Tell me. What were they? Tell me. What are the solutions under that potential? Where this is the energy, and this is some flat bottom potential called V0, or flat top potential. And then this is region 1, this is region 2, and this is region 3. And then I'm asking you for this problem, what was the solution in region 2? That's what I'm asking you. And you did this. You've seen it done a million times. Wow, maybe once or twice, but it must have felt like a million because it was so tedious. Tell me.
It's an exponential growth plus an exponential decay.
That's exactly right. Because you know that there's 2 solutions here. One is the exponential dying, and one is the exponentially growing. Now for the exponentially growing, I want you to notice that the exponentially growing is really not exponentially growing. You should think of it like this. It's really the reflection coefficient, because it's kind of like, you know, you're under the well and you're going from the left to the right, and then you're dying like that. But then you hit that wall, you still make it to the other side. But then when you hit that other side, you have a probability to reflect back. And so when you reflect back, then you're back inside and now you're dying again. See? So, you know, so in my mind, they're really both exponentially dying solutions. You know, one is dying, you know, going through it, and the other is when you reflect from the edge of the potential, and then you're dying again. It's like, oh, I'm really dying in here. Okay, but you can also see that sort of growing too if you look at it from the other perspective. Okay, great. So, and that was really easy to write because you just knew that it was, you know, some C e to the minus kappa x plus d e to the kappa x, right? Where kappa, because it's reversed, you have kappa is equal to square root of 2m v naught minus e over h bar, where I've reversed the order of v naught and e. Okay, so you remember all this. It should be vaguely familiar. And that was really easy from last semester. But now it's like super hard. And the reason it's super hard is because I got this arbitrary potential that you don't know how to solve. You don't know how to solve it. There's an arbitrary potential there. And so it's like totally impossible to solve unless you like numerically integrate it on a computer, which is a big pain in the ass. Well, it used to be at least. Okay, so that means this is where WKB comes in. So WKB says to you, well, look, the solution in region 2, you don't have to integrate it on a numerically on a big giant computer. Instead, just use the WKB solution, which is totally trivial and easy. So just plug it right in. And so that's what we do. That's the whole point. So region 2, it turns out we do know the solution using WKB. And we're going to use this idea that, you know, in the tunneling regime, then remember the wave vector is complex. So we call it K is equal to I kappa, where kappa is real, because that's the wave vector in that. And you guys all did this here. It should sound vaguely familiar. And so we're going to do that now in the WKB approximation. So in the WKB approximation, we see that the wave function in region 2 is going to be the part that goes to the right plus the part that goes to the left. And so the part that goes to the right is going to be c over square root of kappa of x times e to the negative, and then we integrate from x1 to x kappa of x prime dx prime. So that's the dying exponential solution going to the right, plus the growing exponential solution, which is really the dying exponential solution coming from the left, which is going to be equal to d over square root of kappa of x times e to the plus x1 to x kappa of x prime dx prime, where we have used this idea that k of x is equal to the normal k of x is now I kappa x, where kappa is real and kappa of x is equal to the square root of 2m. I reverse the order, v of x minus e, because this is the tunneling regime where v is bigger than e over h bar. Okay, so that's what we do. And so now to get t, so then we want t of e. For the real problem, okay? So so t of e is what? I just gave you the wave function in the 3 regions, region 1, 2, and 3, and you can see all those constants, the coefficients. And so what is the thing that we're trying to solve for? T of e is equal to what? Tell me.
F squared.
Say it again.
F squared.
Good. That's right. It is f squared, except there's a little nuance, which is the fact that notice the normalization, because to get the probability to come through, you have to divide the amplitude to get through divided by the amplitude to go in. That's the actual definition. And so notice how I put an A here. And so what is the transmission coefficient? You're close, but you're missing one thing. Because it's always the ratio. It's always like the ratio, the probability to get through is always the ratio of how many particles come through divided by how many particles were incident. So, because I could send 37 million particles at it and maybe only 12 million get through. So if I shot 37 million particles at the barrier and 12 million got through, what's the probability to get through? Tell me.
The 2 subtracted divided by the bigger one.
Yeah, it's going to be 12 over 37. So okay, so now using that reasoning, tell me what's the transmission coefficient in terms of the wave function in regions 1, 2, and 3.
F over A.
Exactly, but
Squared.
not just say it again.
F
What?
over A quantity squared.
Exactly. That's it. And you guys actually did all this, I think, last semester or something similar. That's it. Perfect. Okay, and so then we got to find F and A, right? And how are we going to do that? Well, I won't drag you through that again. It's the boundary conditions. That's how we do it. So let's do the boundary conditions, because our boundary conditions are, we have boundary conditions at x equals x1 and x equals x2. And so I'm running out of space. I want you guys to see that. So at, well, I'll just have to, let's see, I'll draw it again like this. It's, this is the drawing. This is x1 and this is x2, and this is region 1, region 2, and region 3. And so let's do the boundary condition at region 1. In region 1, the boundary condition is, the first boundary condition is at point x1. And what is the boundary condition at point x1? Can you tell me? In terms of the wave function, I have psi of 1, I have psi of 2, and I have psi of 3. What's the boundary condition at x1 in terms of those wave functions? Well, I'll give you a hint. Psi in region 1 at x1 is equal to what?
Psi 2 of x1.
Yeah, exactly. Because that's continuity of the wave function. Perfect. So let's do that boundary condition. And so that means then let's just plug it in. So you see psi 1 up above. So psi 1 is going to be, okay. But before I plug it in, let's do a little trick. The trick is that WKB works best when the energy is big. And WKB works best when we sort of don't have to worry so much about reflections, because reflections make things complicated. So let's assume E is big, and when the energy of a particle is high, it means it's barreling along with a lot of energy, like a Mack truck. And you know, Mack trucks tend not to reflect off of things; they just kind of smash their way through. And so let's assume then that the reflections are small. But how does that manifest itself in the actual wave function? So in the wave function, we have two parts that indicate, that represent the probability to reflect. One part is up here on the top, it's B, right here, I'm going to underline it. Boom. So that's a reflection in region 1. But we also have a reflection in region 2, which is this guy, D. The exponentially growing part is really a reflection, because that's what happens when the particle hits the right-hand wall and reflects back, and then it goes back dying and back the way it came. So those are two parts of the wave function that both represent probability, or the amplitude to reflect. And so the trick that we're going to do to make this problem easier is we're going to assume what? What's our new approximation that we're going to make? Tell me. This is really, you know, I'm asking you to think like a physicist, you know, because this is really what you do out in the real world. As physicists, as a practicing physicist out in the real world, you're confronted with problems that are always way too complex to solve. And so you're always just struggling, thinking, what can I approximate? What can I approximate? You're always trying to make approximations. I mean, that's what we do. And so now I'm asking you to do it. So what approximation should we make to solve this very difficult problem?
We set C to be 0.
Say it again, please. Say it again, I didn't hear it.
I said set C to be 0.
Which one?
The C
Well,
in side 2.
okay, but C is the one that represents the exponentially decaying one. So that's the probability to move to the right. So that's not a reflection. That's the forward propagating solution. That does not represent the reflection. So it's the reflection that we want to get rid of. But you're close. Which parts of the wave function represent reflection?
Oh, the other one?
That's right. That's right. D. So what are we going to do with D?
That's 0.
That's right. Perfect. But that's not the only part that represents reflection. There's another part in the wave function that represents reflection. What is it? That's not the only reflection in that wave function. There's a part in wave function part 1 that represents reflection. What part is it? And what should we do with it? Tell me.
We can let B equal 0.
Yes, perfect. D equals 0 and B equals 0. That's the trick. Okay, so now when we make that approximation, the wave function at point x1 can be written as a e to the I k1 x1, where we know k1 is just the energy, square root of 2mu over h bar. That's psi1 in region 1, and we know psi2 in region 2. That's just that c e to the whatever. So region 2, it's going to be c over square root of k, I'm sorry, not k, but kappa x1 times e to the negative integral x1 to x1 kappa of x prime dx prime. What is that? What is this integral? What's the integral from x1 to x1? Tell me.
0.
0.
Yeah. Perfect. Equals c over square root of kappa of x1. That's right, because and that's e to the 0, right? E to the minus 0. Okay, and so then we can solve this to get a. So from this, what we're going to do is we're going to say a. We'll solve for a. A is equal to c e to the minus I k x1 over square root of kappa of x1. Okay, we got a, that's nice. And so now that's what we got. So now let's go to x2. And remember, the thing that we're trying to solve for is the ratio of f over a. So hopefully now, from the boundary condition at x2, we're going to get f. And let's do it. So at point 2, we're going to have psi. We're going to have the wave function in region 2 at x2 is equal to what? Tell me. The wave function in region 2 at the point x2 is equal to what?
Wave function region 3 at x2.
The wave function at what?
In region 3 at x2.
Perfect. That's exactly right. That's exactly right. So let's just plug those in that boundary condition. And from those wave functions, we can see that in region 2, it's going to be c over square root of kappa x2 e to the negative integral Now it's gonna be x1 to x2. Oh ho, it looks a little different now, the integral. Can't ignore it anymore. And that's the wave function in region 2, and the wave function in region 3 is gonna be f e to the I k x2, because we've evaluated at the point x2. There you have it. And so now let's just solve for f. So then we can see that f is equal to c e to the minus I k x2 over square root of kappa x2 times e to the negative x1 to x2 kappa of x prime dx prime. Okay, there you have it. That's f. And now to get the transmission coefficient, we just got to do the ratio of f over a and squared. F over a squared. And so let's just do it. So f, it's some tedious writing, but let's just do it. It's going to be c e to the minus I k k. Did I get these k's right? Okay, wait, that's k1. Sorry. K1. Get all the little things right. K1 x2 e to the negative integral x1 to x2 kappa of x prime dx prime divided by there's going to be a square root of kappa of x2, right? And now I have to divide by a, and so when I divide by a on the bottom, I'm going to get c e to the minus I k1. Oh, I dropped all those little, oh shit. K1 x1 times, now I'm going to have a square root of kappa of x1 here, and I'm going to take the absolute magnitude and square it. Okay, that's it. Now, okay, now first let's notice when I take the absolute magnitude and square it, what's going to happen to these complex exponentials? What are they going to turn into?
1.
That's right. And what's going to happen to those c's? What's going to happen to these c's? What are they going to do? What are they going to do?
They cancel.
Well, exactly. So we cancel them. What happens to these kappas? Oh, this is a little more subtle. What happens to the kappas? Let's remind ourselves what kappa is. Where will I draw kappa? Here. This is the problem, right? We have some bumpy top thing. We have the energy. This is x1, this is x2, and kappa is defined as square root of 2m v of x minus e over h bar. So what happens to the kappas at x1 and x2? What do they give me? What is the square root of kappa of x1 over the square root of kappa of x2? What does that equal? Tell me.
It's just 1.
Okay, but it's something over something. What goes on top? And like, how did you get 1?
I thought they were the same.
Okay, well, what are they? If they're the same, what are they? What are they equal to?
Square root of 2m e divided by h.
Yeah, but why are like
times I.
why are they the same? Like, how did you're right, but how did you get that conclusion? Like, how do you know they're the same? And it
Actually,
doesn't
I
have,
don't, yeah, V of X is equal to the, I mean, the potential is equal to the energy at that point.
and so then what is kappa at that point? What is it equal to?
So 0.
Yeah, because the wave vector goes to 0 at the classical turning point. That's right. So we have 0 over 0. So you're totally right. But now you can see that it could be problematical. If you were like a real anal retentive mathematician, then you'd be all sort of like, hey, wait a second, you know, there's a 0 on the bottom. It could diverge and blah, blah, blah. And you get all worried and freaked out. But luckily, none of us are anal retentive mathematicians, and we're just physicists, and we don't really worry too much about all these nuances. At least I don't. And then, so what I always say is, if you got 0 over 0, set it equal to 1. Because, you know, it's either 1 or infinity, you know, and so it really depends on some nuances. And so, the point here, the reason why I'm mentioning this is because I just want to mention to you that in the WKB approximation, there's always subtleties associated with the classical turning point. What does the wave function really do at the classical turning point? You know, there's some subtleties, and to really solve those subtleties, you have to do that complicated connection formula. But all that complicated connection formula is just going to tell you, once you do it all, it's just going to say that, you know, 0 over 0 is 1. So let's skip all that complicated stuff and let's just write 0 over 0 is 1. So that's what we're going to do. Cancel those guys. And so then what we end up with is T of E is equal to E to the negative 2 x1 to x2 kappa of x prime dx prime. And that is a huge result, very significant result. It's very famous. So basically, another way of writing is that the transmission coefficient, the probability to get through any barrier in the world is equal to, just make sure I use the right notation. Yeah, it's equal to e to the minus 2 gamma, where gamma is just equal to the integral of the potential at the two, from one classical turning point to the next, from x1 to x2 of kappa of x prime dx prime, where these are the classical turning points. And it is interesting how these classical concepts keep popping up in quantum mechanics, and that always happens. That is a quality of quantum mechanics, because quantum mechanics is built on top of classical mechanics. We're not like dispensing with all of classical mechanics. We're dispensing with just parts of classical mechanics, and we're keeping other parts. Okay, that's the result. And so this is the probability to get through the barrier. Okay, that's it. So it's a huge result. It's a really big result. So now let's use this result in the most famous example of this result, which is alpha decay.
Quick question.
Yeah,
Why is it V naught or V of X minus E instead of E minus V of X for the kappa?
I'll show you. Where was it? Here it is. It's here when we define the wave function. I'm going to box it right here. Because this is a trick that we always do when we do barrier penetration problems. The wave function is e to the I k of x, but we notice that under the barrier, k is a complex number. When you look at the definition of k, when you have e minus v of x, it's a complex number. And so we define k of x is equal to I kappa of x, where kappa is real. And then we define kappa of x in that way. Okay? Does that look vaguely familiar?
Yeah, thank you.
Okay. Because I know that all of you have done that, but you know, you just, it was a long time ago that you did it, so I don't, you know, I wouldn't have remembered it either. Okay, so all right, let's do alpha decay now. The most famous example of this WKB tunneling formalism. What's alpha decay? Somebody tell me. Does anybody know? What's alpha decay? Does anybody know? Speak up.
Isn't it a helium nucleus breaking out of a bigger nucleus?
Perfect. That's exactly what it is. Good. Excellent. So alpha decay is when you have a chunk of radioactive material, and you'll draw it. It's very easy to draw. So that's radioactive material, like uranium or something. Let's say uranium. And what the old timers noticed is that, you know, what Marie Curie or whoever, all those folks, those old timers, what they noticed is that if you take a chunk of radioactive material, then little particles shoot off of it. Bing, zing. And there are many ones, you know, there's many different things, you know, there's electrons and photons, and, you know, you can have electrons, photons. Well, electrons are beta, photons are gamma, and then you have alpha particles, all right? And so this is the one we're going to focus on today. The alpha particles, you get these little alpha particles jump out, and the alpha particles, they notice, are equal to bare nuclei of helium, which is 2 protons and 2 neutrons. So that's a helium-4 nucleus. That means that Z equals 2 and mass equals 4. Okay, so it has 2 protons and 2 neutrons. These are P equals proton, N equals neutron. All right, so that's an alpha particle. Alpha particle is equal to a helium-4 nucleus. And that's what they noticed, you know? And it was like, wow, that's weird, you know? I mean, who would have guessed that, right? And so then what they noticed also, they did experiments because they were very smart. Those old timers were very, very clever. And one of the things they did was they would catch these alpha particles as they jumped out in detectors. And in the detectors, you know, like a detector can like measure current. You can make detectors in various ways. And in the detector, they could detect, measure energy and the number of particles per time. And the number of particles per time is what we can call the rate. We'll call that the rate. And so if I plot this rate, the rate at which the particles escape, they're shooting out, they notice that that if they plot the rate of the particles versus the energy, they notice that the high energy ones escape more quickly. So they notice this, that the rate that the high energy particles get out more quickly. And they also notice that there's a decay with time, you know, a decay with time, but we're not going to get into that. We're just going to focus on this, that they notice that the high energy particles, the high energy alpha particles shot out more quickly, like at a higher rate. And so this rate I'll call 1 over tau, where tau is a time. And I can define my tau which is the inverse of this rate, I'll give it a name. What will I call it? Can anyone guess? Let's give that time a name. Just, I can measure the rate with an experiment, you know, with the detector, and I can invert the rate and turn it into a time. And if it's a time, what do I call that time? Can you guess? It has a name.
Is it half-life?
Yeah, yeah, or we'll call it, let's call it the lifetime. Yeah. Right, it's the lifetime or half-life or whatever you want to call it. Right, it's the lifetime. So we'll call that the lifetime. It's just a definition. Okay, so what they noticed then is that if I plot the lifetime, which is the inverse of the rate, so lifetime equals the inverse of the rate. So then if I plot the lifetime of the alpha particles, for the alpha particles, the lifetime is gonna do this. So they can see that as I have higher energy, the lifetime is shorter, meaning that the alphas escape more quickly. So that's what they measured that, but they had no clue. They're like, what the hell is going on? You know, they didn't know how to explain it because they did these kinds of measurements before quantum mechanics was even invented. So it's like Marie Curie, I don't think she knew quantum mechanics. When was she doing? Does anybody remember when Marie Curie was doing all her stuff? I can't remember the date. Do any of you know the date? Like when did she discover, you know, radioactivity and all that kind of stuff? Well, okay. Well, if any of you remember it or Google it, you know, interrupt me and just let me know. But I'm pretty sure it was before quantum mechanics was invented. And so the person who solved this problem with quantum mechanics, the person who figured out what the heck is going on using quantum mechanics was a person named, anybody know? Do you know? I'm just curious. Anybody know who it was? There was a person named Gamow. I don't know how to even pronounce that, but it's a famous person. Gamow. Very famous guy. And he did it in 1928. And he used quantum mechanics to solve this problem. And he was a very smart guy. And this was the first application of quantum mechanics to nuclear physics. First application of quantum mechanics to nuclear physics. So that's significant too. You know, because this is the kind of stuff that you need to know if you want to make a nuclear bomb. All right. So this is how it works. So okay, this was the road to nuclear weaponry, and that's true. And so what you need, what he did was he said, okay, I've got this nucleus. Let's think of the nucleus as a big bag, a box. And you know how I am about boxes. I love to think of everything as a box. Quantum mechanics is easy when you think of boxes. So the nucleus is a box. And then I have the alpha particle, which is the 2 protons and the 2 neutrons, is bouncing around in that box, rattling around. And then eventually it escapes. I'm free. I'm free. Yay. So eventually it escapes. Okay. So he said, okay, well, that's the picture. So what is the box? And how do I describe this using quantum mechanics? And so that's what he did. He said, he just made an ansatz, an assumption. He said that the simplest box, let's do this in spherical coordinates. So the simplest box is I have a square well that goes up, and it's attractive. And so so what we're doing is we're plotting, this is V, and then this is R, the radial component, and he says inside it's attractive. So here I have minus V naught, just a flat bottom well, very strongly confining, attractive. Okay, and this is 0 here, so you can see it's negative. And so this is the size of the nucleus, we'll call it R1. And then he says, okay, the nucleus, let's say that the nucleus has a bunch of protons in it. The nucleus has Z protons, then it has a charge of plus ZE. Okay, so the alpha, so I'll call it Q sub big N, but the alpha particle also has a Q. The Q of the alpha is what? Tell me, what's the Q of the alpha? Tell me.
Plus 2E?
Yeah, perfect, thank you. Exactly, so he's saying, I got this, he's saying inside the nucleus, there's this weird attraction. He could not explain where it came from, but he just hypothesized. He said, there's got to be some strong attraction that's keeping the nuclei inside. We'll call that attraction the nuclear force. And that's what it is. It's the nuclear force. And it's very strong and very attractive. And it's just like a box. And that's the nuclear force. That's how you make nuclear bombs. That force is the force that makes a nuclear bomb explode. So that's the force. Okay, so you got this really strong nuclear force, which later they figured out how to use to blow up cities, but he wasn't thinking about that initially. And so that strong nuclear force is just this attractive force, but outside, once the alpha particle gets outside of this crazy, weird, super strong attractive force that he could not explain, it just feels the Coulomb potential. So in this region, so there's two regions, we'll call this region 1, and then there's out here, this is region 2. And in region 2, I'm outside. Once the alpha particle gets outside, then I have this nucleus with plus ZE, and then I have my alpha particle with plus 2E. And once it's outside, and they're separated by some distance R, what is the force between them? What force lives between those two particles? Tell me.
Coulombic.
Yes, exactly. It's just our old friend, the Coulomb force. And that's a force that we all know and understand. It's the Coulomb force. So the Coulomb force is quite simple because the Coulomb force is, there's an energy, a potential, and the potential is quite simple. We all know what it is. It's going to be Q1 times Q2 all over 4 pi epsilon naught times the distance between them, which in this case is equal to 2ZE squared over 4 pi epsilon naught R. Okay, so that's the force between them. There's a potential energy between those two particles once the alpha particle is outside of the nucleus. And so that's this region 2. And so I can plot this. And it's really simple. It's just a simple 1 over R. Okay, 1 over R. Let's just draw it. And then, and that's it. And so that was his picture of the nucleus. He said, I got this weird, inexplicable, but strong attractive force, which is the nuclear force. And then outside of the nucleus, there's going to be a Coulomb force that the alpha particle feels. So that, remember, this is the forces that the alpha particle feels. We're describing the alpha particle. So the alpha particle is rattling around. So now what he said is, okay, the alpha particle is inside this and it has some energy. Let's draw the energy. There's the energy of the alpha particle. So the alpha particle has some energy and it's rattling around inside of there at this energy. And then every now and then it escapes. So how do you describe that quantum mechanically? Well, the first thing to do is to notice that, hey, I got another location here. I'll call that R2. So let's divide this into 3 regions: region 1, region 2, and region 3. Now this should start to look familiar to you. This is just what we did a few minutes ago. No, that's no accident. So we have these 3 regions, and so let's consider region 1 first. Because in region 1, the particle, let's think about this. You know, the particle in region 1, it's just rattling around. It's just going boink, boink, boink. It's just bouncing around. And so let's think about it. Let's think about this in the simplest way possible. Let's just say that it has some velocity in region 1. It has some velocity, and it's just zipping around with some velocity. V equals velocity. And that means that there's a characteristic time, delta t, equals, because it's bouncing around in there, but every now and then it's going to hit the wall, bing, and then it's going to go, and then it's going to hit the other wall, bing, 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 bing. And so the time between collisions, delta t between collisions is going to be equal to, and if this distance is r1 equals the radius of the nucleus, then the time between collisions is going to be the velocity divided by the distance traveled between collisions, which is equal to v over what? V over what? V over, oh, I'm sorry, I got that wrong. I inverted that, I made a mistake. But I still have that question for you guys. The time I got this simple, these simple formulas are the hardest ones. Time is distance divided by velocity. Not, I got that inverted. And so the velocity is just this hypothesized velocity v of the alpha particle. What is the distance traveled between collisions inside the nucleus? Tell me.
R1 divided by V.
Oh, well, I'm asking for a distance. Yeah, what's the distance?
R1.
Okay, good, the radius. But it's not exactly R1 because, but that's close. You know, it's a spherical thing. So this is R1, but between collisions, it has to travel this distance, right? So what is the distance? Tell me.
Oh, 2R1.
Exactly. Good. So now I have the time between collisions. So now I have a frequency of collisions. So now I have the collision frequency, which is the collision, the number of collisions per time is simply equal to 1 over delta t, because there's 1 collision per delta t, which is equal to v over 2r1. Okay, so we have the, okay, so now we know how many times the alpha particle is colliding per time with the wall, blah, 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 blah. And it's purely classical. This is classical picture. But then we say, so now we ask ourselves, what's the probability to escape? And so what we really want is the probability per time. And that's the probability to escape. The probability per time to escape is equal to, this is what we want. We want the probability per time. And the probability per time to escape is going to be equal to the number of collisions per time times the probability per collision to escape. That's equal to the probability per time, right? Okay, so we know that the number of collisions per time, we figured that one out. That's equal to that's equal to V over 2R1 What is this? The probability to escape per collision. What is that? What is that? What is it? What does it mean? What's the probability to escape per collision? What is that? What is that quantity?
That's the transmission coefficient.
Yeah, exactly. Perfect. It's exactly what it is. And how do we get it? How do we get it?
So can we use WKB approximation here?
Yes.
But I have a question. So we assume that the energy is large to use like for the approximations, but here, yeah. So when we say energy is large, is it energy is large relatively when we compare it to the potential at the wall, or like what is? How can we know if it's large enough or no?
Well, first, okay, first let me just tell you the spirit of approximations. Just, as I'm an experimentalist, and so, what I do is I take some data and then I try to solve Schrödinger's equation to explain the data, and I just make a bunch of approximations. And so the first thing I'll just tell you, as a working physicist, what you do is you just make the grossest approximation possible, and then you just see, does it work? You just let's just try it and see if it fits the data. And if it fits the data, then you sort of work your way backwards. And you say, oh, why did it work? It works. So I'm just saying, so in the spirit of that, we would just try it and see if it works. And I'm sure that's what Gamow did, 100 years ago. But now you're saying, because Gamow, I'm just saying that's the spirit of how to do it. You just try it and see. That's the actual best answer to your question is. So I guess the best answer to your question is, who cares? Who cares whether it works? Let's just see. Does it work? But to give you a more serious answer, which is, how do we know that the energy is high enough for it to work? That's a good question. Let me think about it for a moment. I mean, in the last lecture, I did give you a criteria. I wrote down a criteria which was a criteria for momentum, the rate, dv dx, it has to be less than 1, right? So there's some actual criteria that I derived, or I think I told you the answer in the last lecture. And so I don't really have a great answer to your question other than saying that what one could do if one wanted to answer your question is to go back to the last lecture, take that expression that I derived and analyze it in the context of this problem and see if this does indeed satisfy that criteria. And I have not done that. So, but that's that's the only way I can think of answering your question. So I think your question is a good question. It's a hard question though. I'm not, I don't have a simple answer off the top of my head, but to answer that question, that's what I would do, I guess. I can't think of anything better than that. Okay, but let's keep going. So what we see then is that what we have to do is we see that the thing we want is the probability per time to escape, which is going to be equal to V over 2R1 times T of E. And when we talk about the probability per time to escape, we talked about this before in the context of Fermi's golden rule. And so I just want you to remember that probability per time is equal to a rate. It's a rate. So it's a 1 over tau. So this probability per time is 1 over tau because it's probability of 1, like per tau. So how long time does it take for probability to be 1? That's the rate. And so the rate then of escape is V over 2R1 times T of E. And we can even take that, I can invert that as well. I can say now, then I could have tau, I just invert it. And I can say tau is equal to 2 over R1 over V times T of E negative 1. Okay, so I have these two expressions. And this is very significant because these are the experimentally measured quantities. This is what you're measuring. And I want to go back to that because I'm talking about probability per time. And I just want you to realize, like, this is the picture. It's the same picture that, let's see, this is 0. This is B. It's the same picture that you had for Fermi's golden rule. I have some energy. The idea is that the alpha particle is, you got some big blob of probability. Remember the green goo probability? So we have some, you know, at time t equals 0, then this probability is 1 to be inside of the well. So it's a big blob of probability. That's what I'm here. This blob is meant to be probability. But then as time goes on, you can think of the probability is oozing out. It's escaping. The probability is flowing. And I have a detector. As an experimentalist, I have a detector. And what my detector is detecting really is probability, because every time a particle hits the detector, as the probability flows into the detector, that's equivalent to capturing a particle, because the rate of capturing particles is equivalent to the rate at which you capture probability. Remember, because we have this equivalency between probability and particles, and we've discussed that at great length in our scattering discussion, so I'm not going to belabor it anymore, but I just want you to understand that's why calculating probability per time is equivalent to calculating the experimentally relevant quantity. I just want you to sort of see that, because I think it's always tricky to connect the concepts of quantum mechanics to what we actually measure in the laboratory. That connection is sometimes hard to see. Often that is actually the hardest part of quantum mechanics, because the calculations are, for the most part, not that hard once you know what to do. But it's knowing what to do, that's the hard part. Okay, so now we know what to do. So because what we have then is this this situation, and we have this energy. Now we have these 2 points, R2 and R1, and now we want to calculate. We see that it's come down to a tunneling problem, because we need to know now the rate, the transmission coefficient to tunnel. It's for tunneling under the Coulomb barrier. Because this is the tunneling. The tunneling occurs here. So the particle is actually tunneling under the Coulomb barrier. That's what's so cute about this. That's the whole point. The whole point is to figure out what is the rate at which the particle can tunnel under that Coulomb barrier. And it's really this little part right here that he's tunneling under, that little part right there. Tunneling under this. So what is the rate for tunneling under that thing? T of E. Well, it's going to be the WKB. Let's just use WKB. And WKB tells us that the rate to tunnel under that barrier is e to the minus 2 gamma, where gamma is equal to what? It's equal to an integral of kappa of x dx from where to where? From here to here. What are these 2 spots? From where to where?
R1 to R2.
Yeah, exactly. The classical turning points, exactly. And what's kappa? Kappa of x is just equal to square root of 2m. Now it's v of r minus e over h bar. And so the thing is that we know what v of r is. V of r is just the Coulomb, and we calculated already. Where was it? Yeah, it's here. I'm gonna put a box around it. It's this. V of r is 2ze squared over 4 pi epsilon naught r. Just the Coulomb potential between the alpha particle and the nucleus. But there's something else that we know. We also know the turning point, because we know that for the turning point, the classical turning point is when E is equal to V of R1 or R2, V of R2. So R1 is harder. That's the radius of the nucleus, but R2 is easier. This is easy. This is easy to find. This one is hard. Okay, so but R2 is easy because the energy equals V of R2, the classical turning point. So we can just say that E is equal to 2z E squared over 4 pi epsilon naught R1. And so as a result, we know what, R2. And so as a result, we know that R2 is equal to 2z E squared over 4 pi epsilon naught E times the energy. Okay, so now there's a lot of details. Well, not that many details, but we have to, let's remind ourselves what is known and what is not known. What is known, the things that we know are, we know Z, we know the energy, we know R2, okay? And the things that are unknown, let's just remind ourselves what's unknown. Things we don't know. What we don't know is R1. And so R1 will just be, we'll just sort of use it as, say, a fitting parameter, or hopefully it'll go away. Oh, another thing that we don't know is this velocity. Okay, this velocity. We don't know R1, and we don't know that interior velocity. So we'll just call these fitting parameters. Hopefully they'll go away. And so, so let's calculate T of E. So then we must calculate, we have to use quantum mechanics to calculate gamma. And so gamma is equal to the integral of R1, R2 of K of X. And so K of X is going to be 1 over H bar times the square root of 2m V, which is 2z E squared over 4 pi epsilon naught R minus the energy, dr. That's gamma. So all we got to do is this integral. Okay. And so I can parameterize this in terms of R2 because I have this formula for R2. And so I can rewrite this as, I can just rewrite this, and this is just a common way that people do it, but I can rewrite it as square root of 2me over h bar times the integral from R1 to R2 of square root of R2 over R1, I'm sorry, R2 over R minus 1 dr. All right, I've just reparameterized it. It's just a line of algebra. And so I got to do this integral. So you can do this integral. It's not hard, or maybe it's hard, but it's not that hard. Do it with a change of variables. And I'm not going to do it, but it's the kind of, you guys have done integrals this hard in your calculus class. So do it with a change of variables, and then you get an answer. And the answer is that gamma is equal to square root of 2me over h bar times pi over 2 R2 minus 2 square root of R1 R2. Okay, and that's not so hard, but you can do it. But then you say, let's assume that R2 is way bigger than R1. So let's just make the assumption that the radius of the nucleus is really tiny. And so that means that we can ignore this term. That means that this term is small because it has an R1 in it. So then we'll say that this thing is approximately equal to the square root of 2me over h bar times pi over 2 R2. But remember that R2 up here, R2 is proportional to 1 over E. And so that means then that gamma is proportional to square root of E over E is proportional to 1 over the square root of E. All right, and so then what you can see, and so we're running out of time, so I'll just say really quickly, we see then that tau of E is proportional to E to the 2 gamma is proportional to E to the 1 over square root of E, which means then that if I plot tau versus E, it's going to go down. Woo. And that explains alpha decay. It worked. It explains the data. And so that was, so he explained the energy dependence of the lifetime of the alpha particle. He explained all the physics. It all worked beautifully. And that's the end of the story. All right. Bye-bye.